Right now, construction is complete on a machine that defies common sense. It is a camera so wide it covers a patch of sky larger than the full moon in a single shot. It can detect light from galaxies so far away that the light we will capture left before Earth even existed. And compared to the most famous space telescope in history, this new machine does in 1 year what that older telescope could not finish in 1,000. We are going to travel through the cosmos with this telescope. We will peer through walls of cosmic dust. We will watch stars explode in real time. We will find thousands of new worlds hiding in the dark. We will map the invisible skeleton that holds the entire universe together. And we will hunt for answers to the strangest question in all of science. Why is the universe tearing itself apart? If you enjoy what we explore today, hit like and subscribe. It helps more people find these journeys, and there are many more coming. Take a breath. We launch now. Go outside tonight. Look up. Find the moon. That glowing circle hanging in the sky is roughly half a degree wide. For most of human history, capturing that entire circle in a single sharp photograph from space required an instrument the size of a bus. Engineers have now built something that does it in one shot, and then goes wider. NASA's Nancy Grace Roman Space Telescope carries 18 detectors arranged in a tight mosaic. Each detector is 4,000 pixels wide and 4,000 pixels tall. Together, they produce images of 300 megapixels, 6 times the resolution of the most advanced phone cameras ever made, and the field they cover is larger than the face of a full moon. Every single time the shutter opens. Scientists have confirmed this directly from NASA's official mission documentation. 300 megapixels. One image. Sky coverage larger than the moon. But here is where the numbers stop being numbers and start being something harder to hold in your mind. Pause for a second. Hubble Space Telescope has been operating for more than 30 years. In that time, it has built one of the most famous libraries of cosmic images in human history. Deep fields, nebulae, colliding galaxies. It is arguably the most productive scientific instrument ever built. But to photograph the same stretch of sky that Roman can capture in a single year, Hubble would need 1,000 years. 1,000. If Hubble had started this survey when the Roman Empire still ruled Europe, it would not be finished today. Roman is not a better version of Hubble. Hubble is a spotlight, narrow, precise, extraordinarily deep. Roman is a floodlight. It floods the entire room at once, every time it looks. And what it sees in infrared, light your eyes cannot detect. Light that carries information from the earliest ages of the universe. Light that slips through cosmic dust walls that would stop any other telescope cold. Wait, that dust wall matters more than most people realize. Between us and the dense, star-packed heart of our galaxy sits a barrier, enormous clouds of tiny particles drifting across the galactic plane for millions of miles. Visible light cannot pass through it. To standard optical telescopes, the center of the galaxy is simply darkness. Roman's infrared vision punches straight through, the way a radio signal passes through walls. The most crowded, most mysterious region of our galaxy, sealed off for decades, is about to open. Scientists genuinely do not yet know what is hiding inside those dust clouds. They have theories. Roman will find out if any of them are right. Roman finished construction on the 25th of November, 2025. It is now in testing. It is scheduled to launch on a SpaceX Falcon Heavy rocket no earlier than fall 2026, heading to a point 1 million miles from Earth. 1 million miles. And the science it will carry out from there, the questions it is built to answer, may rewrite everything we think we know about how the universe ends. But before we get to the end of everything, we need to meet the woman whose name this telescope carries, because her story is just as extraordinary as the machine itself. In the 1960s, a young astronomer walked into a meeting at NASA and proposed something most people thought was science fiction: a telescope above Earth's atmosphere, free from the blurring interference of weather and air. Her name was Nancy Grace Roman. She became NASA's first chief astronomer and its first female executive. That title matters less than what she actually did. She built the committees, she fought for the budgets, she assembled the engineers and the astronomers and the politicians needed to turn a wild idea into a funded mission. Those efforts, across years of quiet, persistent work, eventually became the Hubble Space Telescope, the most famous scientific instrument in human history. This is confirmed history. Nancy Grace Roman died in 2018. She never saw her name on a telescope. NASA gave it to her posthumously in 2020. She was told early in her career that there was no room in astronomy for women. A supervisor told her directly. She ignored it. She spent the following decades building a legacy so consequential that a multi-billion-dollar machine now carries her name 1 million miles into space. Now here is the part that deserves to land. The telescope named after her is built on her personal philosophy. Roman believed the universe should belong to everyone, so every image, every survey, every data point the Roman Space Telescope collects will be released publicly the moment it is processed. No waiting period, no exclusive access for any team, no proprietary period of any length. Any astronomer anywhere on Earth can download it the same day it arrives. That is unusual. Most space observatories hold data privately for up to a year, protecting the research teams that invested years earning observation time. It is a reasonable system. Roman abandons it completely. Think about what that means in practice. A graduate student at a university in a country with no space program can access the same Roman data as a senior researcher at a major institution. On the same morning, from the same public archive, the universe made accessible to anyone willing to work on it. NASA has explicitly committed to this open data policy for Roman as part of what the agency calls gold standard science. This is not a promise that might change. It is built into the mission design. Roman's data will be so voluminous that no single team could analyze all of it in a year anyway. Hundreds of research groups working in parallel, each extracting different science from the same images, will multiply the total yield far beyond what proprietary access would allow. Roman is built to produce more knowledge than any one group could consume. She built the door to space-based astronomy. Her telescope is about to open it for everyone. But before Roman reaches space and begins delivering that data, it had to survive something no telescope should ever have to face: a fight over its own existence. Not a technical failure, not an engineering setback. A political decision to cancel it entirely. And the story of how that fight played out is something every person who cares about science should know. Great science does not protect itself from politics. Roman has spent over a decade surviving both. The story starts with early optimism. In 2016, Congress actually provided more funding for Roman than NASA had even requested, fast-tracking the mission from study phase into active development. For a large space telescope, that kind of legislative enthusiasm is rare. It felt like momentum, like a signal that the country understood the importance of what Roman was trying to do. Then the momentum became turbulence. Budget pressure became a constant companion to the mission across the following years. Proposed cuts appeared in federal budgets. Mission timelines shifted. Teams at Goddard Space Flight Center worked through uncertainty year after year, continuing to build hardware while the funding picture changed around them. This part is confirmed and on the public record. In the spring of 2025, the administration proposed cutting NASA's science budget nearly in half, from roughly $7.5 billion down to $3.9 billion. As part of that proposal, the White House Office of Management and Budget recommended cancelling Roman entirely. The announcement arrived in the scientific community like a physical blow. Here is why that matters beyond the dollars. Roman is the top priority mission, identified by the Astronomy and Astrophysics Decadal Survey, the consensus document the American astronomical community produces every 10 years. Thousands of researchers participate in that process. They debate priorities. They evaluate missions. They build agreement across institutions and disciplines. The result carries real authority. It is the field telling the government what matters most. Cancelling Roman would not just end a telescope. It would signal that the United States government no longer considers itself bound by the scientific priorities its own scientists establish through that process. It would break a relationship between science and government that has produced some of the most important discoveries in history. Pause and sit with that. As of February 2026, the proposed cuts are still being debated in Congress. The outcome remains uncertain. That is not a comfortable sentence to write, and it is not a comfortable one to hear. And yet Roman's team at Goddard never stopped working. Construction completed on schedule in November 2025. Testing is proceeding. The telescope does not know about budget documents. It only knows whether the next test has started. There is something quietly powerful about that. The engineers who spent years aligning Roman's detectors, calibrating its mirrors, designing its coronagraph, built it anyway. Because the universe does not pause for political uncertainty. Dark energy is still accelerating the cosmos right now. Hidden planets are crossing distant stars right now, creating signals that last only hours. Every month of delay is a month of data that simply ceases to exist. The method Roman uses to hunt those hidden planets, bending light through gravity itself, is strange enough that even Einstein doubted it would ever work. He was wrong. And what Roman will find because he was wrong may answer one of the oldest questions in human history. Albert Einstein predicted it more than a century ago. He then doubted anyone would ever actually measure it. He was wrong. When a massive object sits between us and a distant light source, its gravity bends the light, traveling around it. The object acts as a natural lens, focusing that light and making the background source appear brighter from our perspective. Einstein called it gravitational lensing. He thought the stars were too far apart for this to be useful. Astronomers have now built an entire science around it. Gravitational microlensing is confirmed physics, observed repeatedly. More than 200 exoplanets have already been discovered using this method, verified by multiple independent research teams. Here is how it works in practice. A foreground star drifts in front of a more distant background star, as seen from Earth. The foreground star's gravity bends the background star's light, causing it to briefly appear brighter, sometimes by a factor of several times. If that foreground star has a planet orbiting it, the planet adds its own, smaller, brightening on top, a tiny deviation in the curve, hours to days long. Miss that window and the data is gone. The event never repeats. This is why Roman will stare at hundreds of millions of stars every 12 minutes during its galactic center survey. Not because of any specific star, because microlensing events are rare per individual star but common across a large enough population, and catching them requires near constant watching. Scientists have designed Roman's galactic bulge time domain survey to observe 6 fields toward the center of our galaxy, revisiting them every 12 minutes during 6 observing seasons spread across the 5-year mission. This cadence is not a guess. It is the result of years of calculations about how often these events occur and how long they last. Now think about the scale. Hundreds of millions of stars, every 12 minutes, 6 seasons. The volume of data this produces exceeds anything astronomers have ever had to process. The system detecting these events will be automated software, algorithms scanning light curves in near real time, flagging the distinctive brightness patterns that indicate a lensing event and alerting scientists to follow up. Most events Roman catches will be caused by stars alone, but scientists project that over 1,000 will carry the additional fingerprint of a planet, And the planets microlensing finds are exactly the ones every other method misses. Planets far from their stars, planets in long orbits, planets with no star at all. Wait, planets with no star at all. That is not a mistake. There are planets floating free in the dark between stars. No orbit, no warmth, no destination, just drifting through the galaxy on paths that will carry them for billions of years without ever arriving anywhere. How many of these rogue planets exist is genuinely one of the deepest open questions in planetary science. Some models predict they outnumber the planets that still orbit stars. Others put the number much lower. We have no reliable count. Roman will build that count, and when it does, the number may be deeply unsettling. Between the stars, in the vast cold emptiness that makes up most of the galaxy, something drifts. Full-sized planets, some larger than Jupiter, some closer to Earth's size, moving through interstellar space with no star to orbit, no warmth to receive, no system to call home. Just darkness and motion, stretching across billions of years. We know these objects exist. A handful have been confirmed. But here is what scientists genuinely cannot tell you: how many there are. Current estimates range from a few per star to more than 10 per star. The uncertainty spans an enormous range and reflects how little observational data currently exists. This is a confirmed unknown, not a gap that will be filled by more careful thinking. It requires more observations. They are called rogue planets, or more precisely, free-floating planetary mass objects. Most are thought to be worlds that formed normally inside young solar systems and were then thrown out during the violent early period when giant planets were migrating inward and outward, pulling gravitationally at everything around them. A forming solar system is chaotic. Interactions between large planets can fling smaller ones out entirely, and those worlds never come back. Picture a solar system in its first few million years. Giant planets forming, shifting, colliding with their own gravity. The chaos is real and confirmed by simulations. In many modeled solar systems, one or more planets get ejected completely. They cross the outer boundary of the system and keep going, into the dark, forever. Some researchers believe our own solar system may have ejected one or more planets in its early history, possibly a fifth giant planet between Jupiter and Neptune that was thrown out billions of years ago. This remains a serious scientific theory supported by orbital mechanics modeling, though it has not been confirmed. Now, pause on what that means. The planet you might be standing on, the stable, habitable world with liquid water and breathable air, exists in part because of which planets survived the chaos and which ones were thrown away. Earth is here because the solar system's early violence went a certain way. Somewhere out there, in the cold between stars, may be a world the same size as Earth that lost that lottery. Roman will find these worlds through microlensing. When a rogue planet drifts between us and a background star, it creates its own lensing event, a brightening that lasts hours to days depending on mass. There is no host star producing a competing signal. The event is brief, clean, and distinctive. Based on published microlensing rate models and Roman's confirmed observing cadence, scientists Project Roman will find dozens to hundreds of rogue planets over its 5-year mission. These are scientific estimates based on established physics, not guarantees, but they are the best projections the field can currently produce. What that census tells us about our own solar system's history and about how rare or common stable planetary systems actually are, is a question that may not have a comfortable answer. And compared to what Roman will find when it looks away from stars entirely, rogue planets are almost familiar. Point a standard telescope toward the center of our galaxy, and you see almost nothing. Not because there is nothing there, because there is a wall in the way. Between us and the galactic center lies one of the most effective barriers in the known universe, a vast complex of dust clouds, each particle smaller than a grain of fine sand, drifting across the galactic plane in enormous concentrations. Visible light cannot penetrate it. Optical telescopes are effectively blind to everything behind it. The heart of the Milky Way, the most densely packed, most ancient, most event-filled region of our entire galaxy, has been sitting behind that wall for as long as telescopes have existed. Astronomers have confirmed this through decades of observation. The galactic center is heavily obscured by interstellar dust that absorbs and scatters visible light, making optical study of the inner galaxy extremely limited. Infrared light behaves differently. Its longer wavelength slips between dust particles the way a low-frequency radio wave passes through a concrete wall. Roman's infrared detectors are tuned precisely to this advantage. When Roman points toward the galactic center, the dust is effectively transparent. The wall comes down. What is behind it? The core of the Milky Way is a different environment entirely from where we live. Stars are packed so densely that if you lived on a planet in that region, you would have dozens of neighboring stars close enough to cast shadows at night. The sky would never fully darken. The stellar density is hundreds of times greater than in the neighborhood around our own solar system. That density is exactly what Roman's microlensing survey needs. More stars per square degree means more potential lensing events per hour. More events means more planet detections. The galactic bulge is the richest hunting ground in the observable universe for the kind of science Roman is built to do. Roman's galactic bulge time domain survey is specifically designed around this. Scientists have confirmed that the survey will observe hundreds of millions of individual stars repeatedly, with the automated pipeline detecting microlensing events in near real time across the entire field simultaneously. But the Galactic Center survey is not only about planets. The data Roman collects will also reveal the properties of the oldest stars in our galaxy, stellar populations that formed billions of years before our solar system existed. Their chemistry, their ages, their distribution will tell scientists about the earliest period of galactic formation, when our galaxy was young and violent and building itself out of colliding clouds of hydrogen. And there is something else confirmed at the center of the galaxy, a black hole, roughly 4 million times the mass of a large star, sitting at the precise geometric center of the Milky Way, surrounded by a dense cluster of stars orbiting it at astonishing speeds. Its discovery earned the Nobel Prize in Physics in 2020. Roman will not study that black hole directly, but everything around it, the stars, the dust, the hidden planets, will pass through Roman's field of view. And what Roman finds in that region may answer questions about how galaxies and their central black holes grow together. What is happening at the very edge of that black hole's influence is where things start to get genuinely strange. Most telescopes take photographs. Roman takes a film. The distinction matters more than it sounds. A photograph captures a moment. It freezes light from a single instant and preserves it. That is how most of space astronomy has worked. Point the telescope, expose the detector, record the image, move on. The universe, in most of our best images, appears static, ancient light, fixed in a frame. Roman is designed differently. Its 5-year mission involves returning to the same patches of sky again and again, days apart, months apart, years apart, so that scientists can compare what has changed between visits. A star that flickered, a galaxy that brightened, a point of light that appeared where none existed before. The universe, watched as a living system rather than a frozen painting. This approach is called time-domain astronomy, and scientists have confirmed it as one of Roman's 3 core science strategies, alongside its dark energy surveys and exoplanet census. The events Roman is hunting in its time domain survey are called transients, phenomena that appear, peak, and fade on timescales of days to months. The most scientifically important of these are a specific type of stellar explosion, so consistent in their peak brightness that astronomers use them as measuring sticks for the entire universe. But before we get to those explosions, pause. Think about what it means to watch the same patch of sky for 5 years. Roman will not just catch events in progress. It will catch events no one knew were coming. An ordinary-looking galaxy that suddenly brightens as its central black hole flares up. A star that begins pulsating at unexpected intervals. A new point of light in a galaxy tens of millions of light years away, appearing, brightening, and fading over 3 weeks. These surprise discoveries are often the most scientifically valuable. They are the findings no one planned for and no one could have predicted. Based on the history of every major survey in astronomy, instruments that return to the same sky area repeatedly consistently produce discoveries that outweigh their planned science goals. Roman, covering more sky than any previous time domain survey, will almost certainly do the same. What those discoveries will be is, by definition, unknown right now. Roman's high-latitude time domain survey will cover a wide area of deep sky well away from the dust-filled plane of our galaxy, watching for transient events across an enormous stretch of cosmic history. It will identify tens of thousands of exploding stars scattered across billions of light years, tens of thousands, each one a data point, each one a measurement of how far away it is and how bright it actually was, each one a window into how the universe was expanding at the moment that explosion occurred. And here is what those explosions, when compared across billions of years of data, will finally reveal: whether the force tearing the universe apart has been constant all along, or whether it has been changing. What that force actually is, and why it frightens physicists, that comes next. There is a type of stellar explosion so reliable, so consistent in its peak brightness, that astronomers use it as a measuring stick for the entire universe. It happens when a white dwarf, the dense leftover core of a dead star, roughly the size of Earth but containing more mass than most large stars, pulls material from a companion star nearby. Slowly, over thousands of years, it grows heavier. Then it crosses a specific mass threshold and detonates in a thermonuclear explosion that briefly outshines an entire galaxy. This type of explosion is called a Type Ia supernova. Scientists have confirmed through decades of observation that these explosions reach roughly the same peak brightness every time they occur. Because astronomers know how bright they actually are, comparing that to how bright they appear from Earth gives the exact distance to the explosion. This is one of the most reliable distance measurement tools in all of cosmology. That technique, applied in the 1990s to a few dozen supernovae, produced one of the most shocking discoveries in the history of science. The universe's expansion is speeding up. Astronomers expected the expansion to be slowing down. Gravity pulls things together. The matter in the universe should be acting as a brake on its own outward flight. Instead, the opposite is happening. Galaxies are flying apart faster and faster, as though something is pushing them, overcoming gravity across every scale. That discovery won the Nobel Prize in Physics in 2011. The force behind it was named dark energy, and it remains, to this day, one of the most profound mysteries in all of physics. Here is the honest truth. We have no direct detection of dark energy. We cannot measure it in a laboratory. We have no confirmed theory of what it actually is. We know it exists only because of what it does to the universe's expansion. Its true nature is entirely unknown. Roman's time domain survey will detect tens of thousands of these exploding stars, spread across billions of light years and billions of years of cosmic history. That number is not a luxury, it is a necessity. You need enormous statistics to precisely measure how the expansion rate has changed across different eras. Comparing supernovae from the early universe to those nearby reveals how dark energy has behaved over time. And here is what makes this urgent right now. Recent results from a major galaxy survey called the Dark Energy Spectroscopic Instrument, announced in 2024, hinted that dark energy may not be constant. The strength of whatever is pushing the universe apart may be shifting over time. The statistical confidence was not high enough to declare a confirmed discovery. Scientists are treating it as a serious hint that needs further investigation, which is exactly what Roman is designed to provide. If dark energy is changing, the implications reach beyond any equation. A strengthening dark energy means the universe's expansion could accelerate without limit, eventually pulling apart not just galaxies, but solar systems, planets, and finally atoms themselves. That scenario has a name. Scientists call it the Big Rip. It may not be the most likely end, but it is a real possibility within current physics, and Roman was built specifically to find out whether we are heading there. What the universe is actually made of, the invisible ingredients that dominate it, is even stranger than an accelerating end. Everything you have ever seen, every star, every galaxy, every planet, every nebula in every photograph ever taken, adds up to less than 5% of everything that exists. The rest is dark, invisible, undetectable by any instrument designed to capture light, and yet without it, galaxies would fly apart. Dark matter is confirmed to exist through multiple independent lines of evidence. Galaxies rotate in ways that only make sense if there is far more mass than the visible stars and gas can provide. Galaxy clusters bend light more strongly than their observable contents could produce. The large-scale structure of the universe, the web of filaments and voids that organizes matter on the grandest scales, only forms the way it does if something invisible is scaffolding it. The scaffolding is dark matter. The deep mystery is what dark matter actually is. Candidate particles have been proposed for decades. Weakly interacting massive particles, hypothetical objects that interact with ordinary matter only through gravity and the weak nuclear force. Axions, incredibly light particles left over from the early universe. Sterile neutrinos, heavier cousins of the ghostly particles that pass through ordinary matter by the trillions every second. None of them have been directly detected, despite enormous experiments designed specifically to catch them. The identity of dark matter is one of the deepest open questions in modern physics. Every candidate particle remains unconfirmed. Roman will not detect dark matter directly. No telescope can, because dark matter produces no light. What Roman will do is map where dark matter lives, how it is distributed across the universe, and how that distribution has changed over cosmic time. And it will do this through one of the most elegant techniques in all of astronomy. When light from distant galaxies travels toward us, it passes through regions of space dense with dark matter. That dark matter's gravity subtly bends the light's path, not enough to create dramatic arcs or multiple images, but enough to slightly distort the apparent shapes of the background galaxies. A galaxy that is actually circular may appear a few percent elongated in a particular direction. The effect is tiny, invisible in any single galaxy, but across millions and then hundreds of millions of galaxies, the pattern of distortions becomes a fingerprint. It tells you where the dark matter is concentrated and how massive those concentrations are. This technique is called weak gravitational lensing. It has been used by previous surveys, but never at the scale Roman will achieve. Roman's wide area survey will cover more than 5,000 square degrees of sky, roughly 12% of the entire celestial sphere, building the most detailed weak lensing map of the universe ever assembled. If the map matches our predictions, we learn something powerful. If it does not match, if dark matter is distributed differently than every simulation says it should be, we may have to rethink everything we believe about what matter actually is. And the structure dark matter builds, the vast invisible skeleton of the universe, is even harder to picture than the dark matter itself. Zoom out far enough and the universe stops looking random. The galaxies are not scattered evenly. They cluster in enormous groups and chains, stretched into filaments hundreds of millions of light years long, surrounding vast empty regions called voids where almost nothing exists. The pattern looks At cosmic scale, like a three-dimensional web, strands of matter connecting dense knots, with enormous dark bubbles of emptiness filling the space between. This structure is called the cosmic web, and it is well established by observation. Large galaxy surveys over the past 2 decades have mapped it in increasing detail across enormous volumes of space. It is not a theory. It is something we have seen. But the cosmic web is not just a description of where galaxies happen to be. It is a fossil, a record of the physics of the early universe, written across billions of light years. The filaments and voids grew from tiny fluctuations in the density of matter that existed in the first fractions of a second after the universe began. Regions that were slightly denser than average attracted more matter through gravity, grew denser still, and eventually became the filaments and clusters we see today. Regions that were slightly less dense lost matter to their neighbors and became the voids. The dark matter scaffolding controlled everything. Where dark matter clumped, galaxies followed. Where it was sparse, galaxies did not form. The cosmic web is, at its foundation, a map of dark matter's early distribution drawn out across billions of years of gravitational evolution. Roman will trace this web across cosmic time. Its survey of hundreds of millions of galaxies will build a three-dimensional volume, with depth encoded by distance, that shows how the web has changed from the early universe to today. Think about what that means in practice. Roman will give scientists a picture of the cosmic web, not just as it exists now, but as it existed 1 billion years ago, 3 billion years ago, 6 billion years ago. Comparing those snapshots tells you how fast the web has grown, how dark matter has moved, and whether the growth rate matches what gravity alone predicts, or whether dark energy's influence is visible in the structure itself. This is one of the primary science goals of Roman's high-latitude wide-area survey, confirmed in the mission's official science design documents and reviewed by scientists across the globe. And there is something else hiding in the cosmic web, something frozen into it from the very first moments of cosmic history. Ancient sound waves, still visible today as a subtle pattern in galaxy positions. Wait, sound waves in space, not the Hollywood kind of sound that does not exist in a vacuum. Real pressure waves, rippling through the hot dense plasma that filled the universe in its first moments, moving at roughly half the speed of light, carrying energy outward from the beginning, and then, in an instant, stopping, frozen in place, imprinted on the distribution of matter forever. That frozen pattern is still measurable today. It acts as a ruler, and Roman is going to use it to measure the history of the universe with a precision nothing has ever achieved. What those frozen waves reveal about dark energy and about whether the universe's fate is already decided is where this story gets truly terrifying. In the first few 100,000 years after the universe began, everything was on fire. The entire cosmos was a single dense plasma, matter so hot and energetic that atoms could not hold themselves together. Electrons ripped free from their nuclei. Light could not travel more than a short distance before being absorbed and re-emitted. The universe was opaque, a churning, glowing soup of particles moving at extraordinary speeds, and inside that soup, sound waves were moving. Real pressure waves, rippling outward from tiny fluctuations in density, regions slightly more compressed than their surroundings. These waves moved at roughly half the speed of light through the primordial plasma, carrying energy outward the way a bell carries sound through air after being struck. The early universe rang. These pressure waves are confirmed physics. They are predicted by the standard model of cosmology, and their imprint has been measured by multiple independent observatories, including the Planck satellite and the Wilkinson microwave anisotropy probe, using two completely different methods that arrived at the same answer. Then, about 380,000 years after the beginning, something changed. The universe cooled just enough for electrons and nuclei to combine into neutral atoms for the first time. In a cosmological instant, the plasma became transparent, light streamed freely in all directions, and the sound waves, which had been rushing outward, stopped. The medium they were traveling through had changed state. The waves froze in place at the exact distance they had reached at that moment. Pause. Think about what that means. Those frozen waves left their imprint on the distribution of matter across the entire universe. Wherever a wave crest had compressed matter slightly, more galaxies eventually formed. The result is a subtle but real preference for galaxies to cluster at a specific separation, roughly 500 million light-years apart today. This feature is called baryon acoustic oscillations. It is a ruler, a cosmic measuring stick encoded into the large-scale structure of the universe at the moment it became transparent, preserved across 14 billion years of expansion and still readable today in the positions of galaxies. Baryon acoustic oscillations have been detected in galaxy surveys and used to measure cosmic expansion for over 2 decades. The technique is well-established science, not theoretical speculation. Because scientists know the physical size of those frozen waves from first principles, they can measure how large the apparent separation between galaxy clusters looks at different distances, and from that difference, calculate how much the universe has expanded at each era in its history. Each era adds another data point to the timeline of cosmic expansion, and dark energy's fingerprint is in how that timeline bends. Roman will measure these oscillations across an enormous range of cosmic history, reaching back into epochs that previous instruments could not access. More eras, more data points, a more precise curve. And here is what that curve will tell us that we currently do not know: whether dark energy has stayed the same strength across all of cosmic time, or whether it has been shifting, growing, weakening, behaving like something alive rather than something fixed. That answer, when it arrives, will either confirm our best model of the universe or tear it open. And what hides inside the tear is something physicists have been dreading to find. The universe is expanding. That much has been known since the 1920s. What no one expected was the discovery made in the 1990s. The expansion is accelerating. Galaxies are not just moving apart, they are moving apart faster and faster with every passing moment, as though something is pushing them, overcoming gravity at every scale across every distance. That something was named dark energy, and it constitutes roughly 68% of the total energy content of the entire universe. The majority of everything that exists is this unknown force, and we have no idea what it actually is. Here is the honest position of science on this. Dark energy has never been directly detected. It cannot be measured in a laboratory. It does not interact with light. It does not cluster. It is defined entirely by what it does, not by what it is. This is not a gap that will be filled by more careful thinking. It requires a new discovery. The simplest explanation, called the cosmological constant, treats dark energy as a fixed property of space itself. Empty space, in this model, carries a built-in energy density that does not dilute as the universe expands. Every new stretch of space that expansion creates comes with the same amount of dark energy already in it. The more space there is, the more dark energy there is. And the more dark energy there is, the faster space expands. A self-reinforcing cycle. This model fits the data it has for decades, but it has always had a problem. When physicists calculate what the cosmological constant should be based on quantum mechanics, they get a number roughly 120 orders of magnitude larger than what astronomers actually measure. That is not a rounding error. That is the largest discrepancy between theory and observation in the history of science. It remains unresolved, and now something new has emerged. Recent results from the Dark Energy Spectroscopic Instrument, published in 2024, hint that dark energy may not be constant at all. Its strength may be shifting over time, behaving less like a fixed property of space and more like a dynamic field with its own evolution. The statistical confidence was not high enough to claim a confirmed discovery. Scientists are treating it as a serious hint that demands follow-up. Stop and feel the weight of that. Roman is designed to provide exactly that follow-up. Its combined surveys will constrain dark energy's behavior with unprecedented precision across billions of years of cosmic history. If dark energy has shifted, Roman will see the signature in its data. If dark energy is growing stronger over time, the implications reach beyond any equation. In the most extreme scenario, called the Big Rip, dark energy would eventually grow powerful enough to overcome the forces holding solar systems, then planets, then molecules, then atomic nuclei together, everything pulled apart. That scenario may not be the most likely outcome, but it is a real possibility within current physics. And what dark energy is doing to the fabric of space between galaxies is visible if you know how to look. The tool for seeing it is something no human designed. Light travels in straight lines. Every physics class teaches it. Every intuition we have about vision and optics is built on it. It is also not entirely true. Light follows the curvature of space, and space curves in the presence of mass. When light from a distant galaxy travels toward us and passes near something massive, a galaxy, a cluster of galaxies, a dense concentration of dark matter, the fabric of space around that mass is warped, and the light bends with it. The result is a natural lens built into the universe itself. Gravitational lensing was first confirmed during the solar eclipse of 1919, when astronomers measured starlight bending around a massive body exactly as Einstein's general relativity predicted. It has been observed thousands of times since across every scale. This is established, tested physics. There are 3 levels of this effect, and Roman will use all 3. Strong lensing occurs when the geometry is nearly perfect, a distant galaxy almost directly behind a massive foreground object. The result is spectacular. The background galaxy is stretched into arcs, rings, or split into multiple copies of itself, wrapped around the foreground mass like light bending around a glass marble. These dramatic distortions reveal the total mass of the foreground object, including its dark matter, which would otherwise be invisible. Weak lensing is the statistical version. No single galaxy is dramatically distorted. The effect is too small to see in one image. But across millions of galaxy shapes, a pattern emerges. Galaxies that are actually circular appear slightly elongated in a preferred direction, aligned by the pull of the dark matter they passed near. Measuring this alignment across hundreds of millions of galaxies builds a map of where dark matter is distributed throughout the universe. Roman's high-latitude wide-area survey is specifically designed to measure weak lensing across more than 5,000 square degrees of sky, more than 12% of the entire celestial sphere. This is its primary dark matter mapping strategy, confirmed in the mission's science documentation. And there is a third level, microlensing, which we have already discussed in the context of exoplanet hunting. Same physics, smaller scale, individual stars and their planets doing the bending instead of galaxy clusters. Now think about what all 3 together give you. Microlensing maps individual planets and stars. Weak lensing maps the dark matter scaffolding on the scale of galaxy clusters and cosmic filaments. Strong lensing reveals the most massive structures and magnifies the most distant galaxies, letting Roman see objects that would otherwise be too faint. 3 scales of the same fundamental phenomenon, giving scientists a 3-dimensional view of mass distribution across the entire observable universe. And the map that emerges from that view is something no generation before ours has been able to see. A complete picture of how matter, visible and invisible, has organized itself across 14 billion years of gravitational evolution. If that map matches our best predictions, we learn something powerful. If it does not match, if dark matter is distributed differently than every simulation says it should be, something is wrong with our understanding of matter itself. What Roman might find in that mismatch is far stranger than dark matter. 1 billion is a number that resists imagination. If you counted one number per second, it would take you roughly 32 years to reach 1 billion. If you laid 1 billion grains of sand end to end, the line would stretch across the continental United States. And if you tried to individually photograph 1 billion galaxies using Hubble, pointing at one patch of sky at a time, you would need to start now and work until long after every living person on Earth today was gone. Roman will do it in 5 years. Roman's primary survey is expected to measure light from over 1 billion galaxies across its 5-year prime mission. This projection comes from Roman's confirmed field of view, survey strategy, and sensitivity calculations published by NASA's science team. It is not a marketing number. It is the result of engineering. Each of those 1 billion galaxies contains, on average, hundreds of billions of stars. Some contain trillions. Our own galaxy holds an estimated 200 billion, 1 billion galaxies. Each galaxy a universe in miniature, scattered across distances so vast that light from the most distant ones began travelling before Earth existed. Roman's high-latitude, wide-area survey will cover more than 5,000 square degrees of sky, roughly 12% of everything above our heads, in just under 1.5 years of total observation time. Every pointing will capture thousands of galaxies in a single image. The data pipeline running behind Roman's observations will process, catalogue, and archive this flood continuously. But the number alone is not the point. The point is what you can do with 1 billion data points. When you have 1 billion galaxies mapped in 3 dimensions, their positions, their distances, their apparent shapes, their colours, you can reconstruct the history of the universe as a volume rather than a snapshot. Galaxies nearby show the universe as it is now. Galaxies at the edge of Roman's reach show it as it was billions of years ago. The depth of the survey is the depth of time itself. This 3-dimensional approach is called a cosmic tomography survey. It is one of the most powerful tools in modern cosmology and is explicitly built into Roman's survey design, reviewed and approved by the mission's scientific committee. Scientists will use this volume to trace the growth of cosmic structure across time, watching how the filaments and clusters of the cosmic web have changed, measuring whether the growth rate matches what dark energy and dark matter models predict, and flagging any discrepancy that might point toward new physics. And there is something hidden in the positions of all those galaxies, a subtle pattern, frozen in from the beginning of time, that acts as the most reliable ruler in the known universe. We touched on it before. But what it can actually reveal about whether the universe's end is already decided goes far deeper than most people realize. Stop, because what comes next in this story is the part that changes the ending, and it begins with a question about planets that has never had a real answer. In 1990, the number of confirmed planets outside our solar system was 0. Not few, 0. The idea that other stars had their own planetary systems was well supported by theory and strongly suspected by most astronomers. But no one had proven it with observation. The question of whether our solar system was typical or exceptional had no answer. Today, thousands of exoplanets are confirmed, and Roman is about to add thousands more in a completely different part of the galaxy, using a method that reaches worlds nothing else can find. As of early 2026, more than 5,500 exoplanets have been confirmed by various missions and ground-based telescopes. The vast majority were found using the transit method, detecting the dimming that occurs when a planet crosses in front of its star and blocks a fraction of its light. The transit method works brilliantly for planets close to their stars, completing orbits in days or weeks. You can watch the repeated dimming and confirm the signal. But it has a blind spot. Planets in wide orbits, the kind that take years or decades to complete one trip around their star, are nearly impossible to confirm this way. And planets with no star at all produce no transit signal whatsoever. Roman's microlensing survey fills that blind spot. By watching the galactic center continuously, catching the gravitational brightening events that reveal planets as they cross the line of sight to background stars. Roman will find planets at orbital distances from their stars that no transit mission can reach. Long-period planets, cold planets, giant planets in the outer regions of solar systems, in the same kind of orbital territory where Jupiter and Saturn sit in ours. Roman's Galactic Bulge Time Domain Survey is projected to discover over 2,500 new exoplanets using microlensing alone. These projections are based on published estimates from the mission science team, grounded in established microlensing rate calculations and Roman's confirmed observing strategy. But here is what makes this a true census rather than a targeted search. Roman will not be looking for specific types of planets. It will be catching everything the galactic center reveals. Every size, every orbital distance, every host star type. The result will be a population sample large enough to draw statistical conclusions about what kinds of planetary systems the galaxy actually builds. Are systems like ours, with small rocky planets close in and giant planets far out, common? Or is our solar system an unusual configuration? Right now, we genuinely do not know. Whether the arrangement of planets in our solar system is typical or rare is currently unknown. Roman census is one of the most direct ways to find out, and the answer has profound implications for the question of life elsewhere in the universe. Every planet Roman finds will carry information: its mass, its distance from its star, its orbital characteristics. Aggregate enough of those data points, and you build the most complete picture of planetary demographics ever assembled, a true accounting of what kinds of worlds the galaxy makes. And among those worlds will be some that belong to no star at all. Counting them raises a question that goes far deeper than astronomy. It asks something about our own existence. Imagine you are standing in a dark field at night, trying to spot a firefly hovering next to a lighthouse beam. The lighthouse is not just brighter than the firefly, it is billions of times brighter. Even knowing exactly where the firefly is, the light from the lighthouse washes it out completely. That is the challenge of directly photographing a planet around another star. A star outshines any planet orbiting it by roughly 1 billion times in visible light. The planet is there, its reflected light is real. But to detect it, you need to suppress the star's light with extraordinary precision without disturbing the planet's much fainter glow just a fraction of a degree away. Roman carries a coronagraph instrument designed and built at NASA's Jet Propulsion Laboratory in California. It is the most technologically advanced coronagraph ever sent to space. This is confirmed by NASA's engineering documentation. The coronagraph works through a set of precisely shaped masks and mirrors that block incoming starlight at the focal plane, reducing it by a factor of roughly 1 billion. What remains, the light that slips past the mask, can be examined for the faint reflection of a planet. This requires mechanical precision measured in nanometers. A nanometer is 1 billionth of a meter. Human hair is roughly 80,000 nanometers wide. Roman's coronagraph must hold its mirrors to tolerances hundreds of times finer than that, in the vacuum of space, at temperatures far below freezing. The instrument passed all its ground tests. Whether it performs as designed in actual space is something only launch will confirm. Scientists are genuinely waiting on that answer. Roman's coronagraph is officially classified as a technology demonstration on this mission. Its primary goal is to prove that this level of starlight suppression works in space, paving the way for future telescopes designed to use it at full scale. This is a confirmed part of the mission design, not a secondary priority. Even in demonstration mode, it will do real science. It will image select giant planets orbiting nearby stars, studying worlds that are older and colder than the young, hot super-Jupiters that earlier direct imaging missions captured. It will look for the dusty debris disks around other stars, the remnants of planet formation, the cosmic construction sites that reveal how solar systems build themselves. And every performance measurement the coronagraph returns from space will feed directly into the design of the next telescope. A larger instrument, a more powerful one, purpose-built not just to image giant planets, but to photograph Earth-sized worlds in the habitable zones of nearby stars and analyze their atmospheres for the chemical signatures of life. That future telescope has a name. NASA calls it the Habitable Worlds Observatory. Roman named the top priority for this decade. That observatory is the top priority for the next. Roman builds the bridge. What the coronagraph proves in space over the next 5 years will determine whether that bridge can be crossed. And the question waiting on the other side, whether any of those distant atmospheres carry the fingerprint of biology, is one humanity has been asking since long before telescopes existed. But before we reach that question, Roman must first survive its journey to space, and the rocket carrying it is one of the most powerful machines ever built. In the summer of 2026, a rocket will stand at Launch Complex 39 Alpha at Kennedy Space Center in Florida. This is the same pad that sent Apollo missions to the moon. It has carried more historic payloads than any other launch site in history. And on the morning of Roman's launch, it will carry something that may produce more scientific discoveries than anything launched from it before. The rocket is a SpaceX Falcon Heavy. At liftoff, it generates roughly 5 million pounds of thrust from 27 engines burning simultaneously, the most powerful operational launch vehicle currently in regular service. It is loud enough to be felt in the body from miles away, and aboard it will sit the Nancy Grace Roman Space Telescope, folded into its launch configuration, waiting. NASA awarded Roman's launch contract to SpaceX in 2022 for launch atop a Falcon Heavy from Launch Complex 39 Alpha. The total launch contract value is approximately $255 million. These are confirmed figures from NASA's public records. Roman will not go to low Earth orbit, where Hubble operates a few hundred miles up. It will travel to the second Lagrange point, a gravitational balance location 1 million miles from Earth in the direction away from our nearest star. At this point, the gravitational pulls of Earth and its nearest star balance out, allowing a spacecraft to maintain a stable position in a slow halo orbit. More importantly, a sunshield keeps the telescope in permanent cold shadow, which is essential for its infrared detectors to function. The journey from launch to final orbit takes roughly a month. Think about the distance, 1 million miles. The moon is about 240,000 miles away. Roman will travel 4 times further than that and keep going. At highway driving speed, it would take over 100 years to cover the distance. Roman's rocket will do it in weeks. Once Roman arrives at its destination and begins cooling to operating temperature, several months of commissioning and calibration begin before science operations start. Every instrument must be checked, every detector characterized, every mirror alignment verified. The first science images will arrive months after launch. Roman completed construction in November 2025 and is currently undergoing final environmental testing. This testing simulates the vibration of launch, the vacuum of space, and the extreme cold of its operating environment. After passing, it will be shipped to Kennedy Space Center for launch preparations in summer 2026. This schedule is confirmed by NASA's Goddard Space Flight Center, and once Roman begins operating, something unusual will happen that no previous space telescope has done at this scale. Every piece of data it collects, every image, every spectrum, every detection will be released publicly with no delay. The moment the data is processed, it belongs to anyone who wants it. That decision, and the staggering volume of data it will release, will require computing infrastructure unlike anything previously built for astronomy. And the first teams to work with that data will be searching for something most scientists have never directly seen: the invisible skeleton that holds the entire observable universe in its shape. What they find in that data may answer questions, or it may open ones that make current mysteries look simple. they share the same neighborhood in space, 1 million miles from Earth. At the gravitational balance point, called the second Lagrange point, two of the most powerful space telescopes ever built orbit within a few 100,000 miles of each other. One of them is the James Webb Space Telescope. The other will soon be Roman. They are not competing. Understanding why reveals something important about how astronomy actually works and why both are necessary. The James Webb Space Telescope has been operating at the second Lagrange point since 2022. Roman is designed to operate at the same location, giving both access to the cold, stable environment required for sensitive infrared observations. This is confirmed by both missions' orbital design documents. James Webb is depth. Its primary mirror spans over 21 feet, more than 2.5 times wider than Roman's. It stares at individual targets for hours, sometimes days, gathering as many photons as possible from the most distant, faintest objects in the cosmos. When Webb studies a galaxy from the first few 100 million years of the universe's history, it delivers extraordinary detail: the galaxy's chemistry, its temperature, the elements in its gas, the age of its stars. Webb is a spotlight, illuminating one thing at a time with unmatched precision and sensitivity. Roman is width. Its detector array covers a field 100 times larger than Webb's infrared camera. Roman does not stare at single targets for extended periods. It sweeps, it surveys, it catalogues vast populations, measures statistical trends, and maps structures at scales that would take Webb centuries to cover. Roman is the floodlight that reveals the room. Webb is the spotlight that examines what the floodlight finds. Webb's primary infrared camera covers a field of view of roughly 0.04 square degrees. Roman's field of view is approximately 0.28 square degrees, and with Roman's survey strategy, the effective area advantage across a full mission is far greater. These numbers come from each mission's confirmed instrument specifications. The two telescopes are designed to work in sequence. Roman will identify objects of interest across enormous patches of sky. Webb will then be aimed at the highest priority targets for detailed follow-up. Roman writes Webb's to-do list. Webb fills in the details Roman cannot reach. This is not accident. It is design. The astronomical community planned for these missions to be complementary, and the science return from both working together is greater than either could achieve alone. And there is a third telescope already operating that Roman will complement in a different way. The Euclid Space Telescope, launched by the European Space Agency in 2023, is also designed to survey dark energy and dark matter, but with a smaller field and different wavelength coverage. Roman and Euclid will observe overlapping sky areas, and their combined datasets will be more powerful than either separately. Science at this scale is not a competition. It is a collaboration across decades and billions of dollars and dozens of countries. What all of this collaboration is ultimately trying to understand, the invisible force accelerating the universe's expansion, may have consequences for every atom in existence, and recent hints suggest that force is not behaving the way anyone expected. Every great observatory reveals something unexpected. Hubble was launched to measure the expansion rate of the universe. It did that, and also discovered that most large galaxies host supermassive black holes at their centers, revealed the accelerating expansion of the universe, showed that the universe is 13.8 billion years old, and produced images that changed how billions of people think about the cosmos. None of those discoveries were listed in its original science case. Roman will do the same. Based on the history of every large observatory ever operated, surveys at Roman scale consistently produce discoveries no one planned for. What those discoveries will be is, by definition, unknown right now, but statistically it would be extraordinary if Roman did not find something completely unexpected. Here is what scientists do expect, based on the mission's confirmed capabilities. Roman will image the Andromeda Galaxy, our nearest large galactic neighbor, about 2.5 million light-years away, in a handful of pointings. Hubble has studied individual regions of Andromeda in extraordinary detail. Roman will capture nearly the entire galaxy at once, in a single observing session, with Hubble-quality sharpness. The resulting image will contain hundreds of millions of individual stars. Scientists will be able to track the lives of stellar populations across the entire galaxy in a way never previously possible. NASA simulations of Roman's Andromeda imaging capability confirm it would survey the main body of the galaxy roughly 1,500 times faster than Hubble could. That simulation result is published in NASA's science documentation. Roman will also catch things happening in real time that no previous telescope has been fast enough to document at scale. Stellar flares, sudden brightenings of stars that can temporarily sterilize any nearby planets. Tidal disruption events, moments when a star passes too close to a supermassive black hole and is torn apart in a burst of radiation. Gravitational wave counterparts, the light emitted when neutron stars collide, producing both ripples in space and a burst of radiation across every wavelength simultaneously. These events are rare per individual galaxy. Across the thousands of galaxies in Roman's field of view at any moment, they happen constantly. Roman will catch hundreds of each type over its mission, building the largest sample ever assembled of some of the most extreme events in the known universe. Roman's wide field and high cadence make it uniquely suited to catching rare transient events at population scale. This is an explicit secondary science goal of the mission, confirmed in its science documentation. But there is one thing Roman will see that goes beyond any planned science goal. The deep field image Roman will eventually produce by stacking thousands of exposures of the same patch of sky. Every deep field image ever taken has rewritten our understanding of the universe's scale. Hubble's deep field revealed thousands of galaxies in a spot that looked empty. Webb's deep field showed those same galaxies in infrared detail across almost all of cosmic history. Roman's deep field will be wider, far wider, and it will reveal structure at the largest scales that current instruments are simply not big enough to measure. What is sitting at those largest scales, the patterns that only emerge when you see enough of the sky at once, may not match any model currently in use. Most of the greatest discoveries in space astronomy have been gated, at least temporarily, behind walls of proprietary access. The research teams that earn observation time on Hubble or Webb must first write detailed proposals, compete against hundreds of other scientists, wait months for the telescope committee's decision, schedule their observations, and then receive their data with an exclusive 12-month window in which only they can analyze it. This system is reasonable. It protects the enormous investment these teams make. It rewards the science that earns telescope time. Roman will not work this way. Every observation Roman makes will be released publicly with no exclusive access period. The moment data is processed and verified, it enters the public archive. Any scientist anywhere can download it the same day. NASA has explicitly stated this policy in Roman's science documentation, described as a core commitment of the mission. This is genuinely unusual. And the reason NASA made this choice reveals something important about the nature of Roman's science. Roman's data is not designed to answer one question at a time. A single Roman image of a galaxy-rich field might simultaneously contain information relevant to dark energy measurements, dark matter mapping, stellar population studies, transient event detection, gravitational lensing analysis, and potentially exoplanet microlensing. Proprietary access for a single team studying dark energy means that team is sitting on data that dozens of other research groups need for completely different science. The open policy allows hundreds of teams to work in parallel on the same dataset. The dark energy group, the exoplanet group, the stellar evolution group, the black hole group, all starting at the same moment, extracting different discoveries from the same photons. NASA calls this commitment gold standard science. The Roman mission documentation explicitly describes the open data policy as central to the mission's philosophy, not an afterthought, and this commitment has been publicly reaffirmed multiple times. Think about who this reaches beyond established research institutions. Graduate students at universities in countries with no national space program, independent researchers without major funding, scientists at the beginning of their careers who would never win competitive observation time but can contribute to one of the most important datasets in the history of astronomy. Nancy Grace Roman believed the universe should be accessible to anyone willing to work on it. The telescope named after her is the most direct expression of that belief ever built into a scientific instrument. But the volume of data this releases is unlike anything the astronomy community has previously managed. Roman surveys will produce data at a rate comparable to filling the entire text content of the Library of Congress every few days, continuously, for 5 years. Managing that flood, processing it in near real time, making it searchable and usable for thousands of simultaneous researchers around the world, that infrastructure has been years in the building. And when that data starts flowing, when the first Roman images arrive and enter the public archive, what scientists find in the first weeks of analysis may set the direction of astronomy for a generation. Because Roman is not looking at one thing, it is looking at everything at once. And somewhere in everything, something unexpected is waiting. What that something might be, and why the scale of Roman's view makes it uniquely positioned to find it, is where this story reaches its most extraordinary possibility. There are planets out there that have never seen a sunrise, no star to orbit, no warmth arriving from any direction, just darkness, motion, and the cold of interstellar space, temperatures hovering near absolute zero, the lowest temperature the laws of physics allow. These worlds drift through the galaxy on trajectories that began billions of years ago and will continue for billions more without ever arriving anywhere. They are called free-floating planets, or rogue planets, and they are almost certainly far more common than most people realize. How many free-floating planets exist in our galaxy is genuinely one of the deepest unknowns in planetary science. Published estimates range from a few per star to more than 10 per star. The uncertainty spans an enormous range and reflects how little observational data currently exists. This is not something better calculations will resolve. It requires actual observations, which is exactly what Roman is built to provide. Here is how they are born. A young solar system forming around a new star is not a peaceful place. Giant planets form and begin migrating, moving inward, moving outward, pulled by interactions with the disk of gas and dust around the star, and by the gravitational push and pull of neighboring giant worlds. When two giant planets pass close enough to each other, one can steal orbital energy from the other. The winner falls into a tighter orbit. The loser gets flung outward. If the fling is powerful enough, the ejected planet crosses the edge of the solar system entirely and keeps moving into the dark. Forever. Computer simulations of solar system formation consistently produce these ejections. The existence of free-floating planets is expected by theory and supported by a small number of confirmed detections. The exact population size, though, remains a scientific mystery. Some of these worlds are giant planets, far larger than anything in our solar system. Others may be Earth-sized. A few may even retain subsurface liquid oceans, heated not by any star, but by the radioactive decay of heavy elements in their rocky cores. The heat from deep within may keep water liquid in complete darkness for billions of years. The physics of internal heating is confirmed. Whether liquid water in total darkness, with no light energy, could support biology is genuinely unknown. Roman will find these worlds through microlensing. When a rogue planet drifts between us and a distant background star, it briefly magnifies that star's light. The brightening lasts hours to days depending on the planet's mass. Roman's 12-minute observing cadence over the galactic bulge is designed specifically to catch these brief signals before they fade. Based on published microlensing rate models and Roman's confirmed observing cadence, scientists project Roman will detect dozens to hundreds of free-floating planets over its 5-year mission. This would represent the largest sample of such objects ever assembled and the first real foundation for understanding how common they are. When that census comes in, it will tell us something profound about the history of planetary systems in our galaxy. How often do solar systems eject their members? How violent is the formation process, on average? And how many of the worlds in this galaxy have spent their entire existence in the cold between stars, unseen and unknown? The number, when it arrives, may change how we think about what a planet actually is, and it connects directly to a question Roman will approach that no previous mission has had the tools to address. This is the question everyone wants answered. It is the question that drives funding proposals, captures headlines, and pulls people into astronomy who might otherwise never look up. Is there another planet like Earth out there? Roman will not answer it directly, but what Roman does in the next 5 years will determine whether any future telescope can. Roman's exoplanet census, while the largest ever attempted, is not designed to detect Earth-sized planets in habitable zones through direct imaging. The technology to do that does not yet exist in space. Roman is building the statistical foundation and the instrument, proof of concept, that future missions will require. This is a confirmed aspect of how the mission is designed, not a limitation that surprised anyone. Here is what Roman will actually tell us. Its microlensing survey will, for the first time, give astronomers a statistically complete picture of how often planets appear at various masses and orbital distances from their host stars, including the range of distances where liquid water could exist on a rocky world. This is one of the most important numbers in the search for life. How common are potentially habitable planets? Right now, we do not know. Transit surveys have found thousands of planets in close orbits, but their sensitivity drops sharply for longer orbital periods. The habitable zones around stars similar to ours fall right in the range where those surveys struggle most. Roman's microlensing fills that gap. Scientists expect Roman's galactic bulge survey to detect a statistically significant sample of planets at orbital separations comparable to Earth's distance from its nearest star, for the first time providing a reliable occurrence rate for planets in that regime. This expectation is grounded in published science, not optimism. And then there is the coronagraph. Roman's coronagraph will directly image select giant planets around nearby stars, suppressing starlight by roughly 1 billion times. But to image an Earth-sized planet, you need a coronagraph roughly 10,000 times more powerful still. Roman does not reach that level. It gets us measurably closer. The telescope designed to reach it is called the Habitable Worlds Observatory. It is the top priority large mission recommended in the most recent astronomy and astrophysics decadal survey. If funded and built on schedule, it could be operating in the early 2040s. Whether it will be funded, what it will cost, and when it will launch are all currently unknown. The challenges Roman itself has faced illustrate how uncertain large science missions can be. If it launches and works as designed, it will photograph rocky planets around nearby stars and analyze light from their atmospheres, looking for oxygen, water vapor, and methane in combinations that only biology produces. Roman builds the bridge to that moment. Its census tells us whether Earth-like planets are common enough to make the search worthwhile. Its coronagraph proves the technology the future mission needs. Its surveys reveal which nearby stars are most likely to host promising targets. Every planet Roman finds is a data point in the most important calculation in the history of science. Whether we are alone and what Roman discovers, quietly in the background of all that work, may reset something far more fundamental than anyone expected. Somewhere in the universe right now, a star is dying in the most violent way matter can arrange itself. A white dwarf, the cooling remnant of a dead star, roughly the size of Earth, but packed with more mass than most large stars, is pulling material from a nearby companion. Slowly, over thousands of years, it grows heavier. Then, it crosses a specific mass threshold and detonates. The explosion releases more energy in a few weeks than a typical large star will radiate across its entire 10 billion year lifetime. This type of explosion is called a Type Ia supernova. Scientists have confirmed through decades of observation that these explosions reach roughly the same peak brightness every time they occur, because astronomers know how bright they actually are. Comparing that to how bright they appear from Earth gives the exact distance to the explosion. This is one of the most reliable distance measurement tools in cosmology. That technique, applied in the 1990s to a few dozen supernovae, revealed that the universe's expansion is accelerating. The discovery rewrote cosmology. It earned the Nobel Prize in Physics in 2011, but the sample was small. Precision was limited by statistics. To test whether dark energy is constant or changing, scientists need tens of thousands of these events, spread across billions of light years and covering eras of the universe that previous surveys could not reach. Stop here and feel the full weight of that number. This is not a rounding error or an optimistic projection. Roman's time domain surveys are expected to detect tens of thousands of Type Ia supernovae over the 5-year mission, roughly 100 times more than the samples that originally revealed cosmic acceleration. This projection is based on Roman's confirmed field of view, survey cadence, and detection sensitivity. 100 times more. Every additional data point tightens the measurement. Every era Roman can reach adds another point to the curve of cosmic expansion history. And it is the shape of that curve, how it bends, how it steepens or flattens across time, that reveals what dark energy has been doing since the universe began. A constant dark energy produces one specific curve. A changing dark energy bends it differently. Roman will measure that curve across nearly the full history of the universe, from when it was young and dense to the vast, thinning cosmos it has become today. The most recent hints from other instruments suggest the curve may be bending in a way the simplest model does not predict. If Roman confirms that deviation with tens of thousands of supernovae, the implications cascade through all of physics. The standard model of cosmology would need to be rebuilt. Whether dark energy is evolving remains an open scientific question. Roman's supernova dataset is one of the most powerful tests ever designed to resolve it. The answer it produces will be one of the most cited results in the history of the field, and what Roman discovers while building that curve leads directly to the most terrifying possibility the data currently allows. A possibility that physicists have given a name no one wants to think about for too long. Every atom in your body is held together by forces that have existed, unbroken, since the first seconds after the universe began. The bonds between molecules, the forces between atoms, the nuclear interactions holding atomic cores intact. These are not fragile. They are among the most stable structures in nature, persisting across billions of years without interruption. Dark energy, if it is growing stronger over time, could eventually break all of them. The Big Rip is a real theoretical prediction within modern cosmology. It appears in peer-reviewed physics literature and is taken seriously as a possible endpoint for the universe. Whether it is the actual endpoint depends entirely on how dark energy behaves, which is precisely what Roman is designed to measure. Here is how it unfolds in the most extreme version that current physics allows. Dark energy, if it is a growing field rather than a fixed constant, would eventually overpower gravity at smaller and smaller scales. First, galaxy clusters would begin pulling apart as dark energy overcomes the gravity holding them together. Then, individual galaxies would dissolve. Then solar systems would lose their planets. Then planets would lose their moons. Then, growing still stronger, the rocks and oceans and atmospheres of those planets would be stripped away. Then molecules would be torn apart. Then atoms. Then, in the final fraction of a second before the end, atomic nuclei themselves would be ripped open. Everything that exists, every structure, every arrangement of matter that has formed across 14 billion years of cosmic history, gone. This scenario is called the Big Rip. If dark energy is growing at the rate, current hints suggest the timescale for when it would occur would be tens of billions of years from now. Humanity, if it exists at all by then, would be unrecognizable. But the direction matters now, because it determines the physics governing every moment between here and there. Here is what matters right now. Whether the Big Rip is the universe's fate depends on a single measurable parameter: how strongly dark energy is growing over time, or whether it is growing at all. A universe where dark energy is constant ends differently. It expands forever, growing colder and emptier, until the last stars burn out. Black holes slowly evaporate over incomprehensible timescales, and the universe reaches a state of maximum entropy. Cold, dark, silent. A universe that once roared with light and heat, reduced to something barely distinguishable from nothing. That ending, called the Big Freeze, is almost comfortable compared to the alternative. Roman's measurements of supernovae, baryon acoustic oscillations, gravitational lensing, and galaxy clustering across cosmic time will pin down dark energy's behavior with a precision no previous telescope has achieved. The result will determine which ending the universe is heading toward, and the data Roman collects to answer that question will simultaneously build something else, the foundation for the greatest search in the history of science. A search that the woman whose name Roman carries would have recognized immediately as the logical next step. Roman is not the last telescope. It is the one that makes the next telescope possible. The question of whether life exists elsewhere in the universe is the oldest scientific question humanity has never answered. Every civilization that looked at the night sky asked it. Every generation of astronomers worked toward instruments powerful enough to approach it. Roman is the closest step yet taken toward the tool that will finally, directly, look for the answer. The Astronomy and Astrophysics Decadal Survey, published in 2021, named the Habitable Worlds Observatory as the top priority for the following decade of large space missions. Roman was the top priority of the previous decade. The two missions form an explicit scientific chain, each building on the last. This is confirmed in the survey's published recommendations. The Habitable Worlds Observatory will carry a coronagraph far more powerful than Roman's. Its primary mirror will be significantly larger. It will be optimized to directly image rocky planets in habitable zones around nearby stars, and to analyze the light reflected from their atmospheres through a technique called spectroscopy. Spectroscopy breaks light into its component wavelengths. Different molecules absorb light at different wavelengths, leaving gaps in the spectrum that act as a fingerprint. Oxygen leaves a fingerprint, water vapor leaves one, methane leaves one. The combination of oxygen and methane together in an atmosphere is a powerful indicator of biology. Without life continuously replenishing them, those two gases react with each other and disappear within geological timescales. This is confirmed biochemistry and atmospheric science. The challenge is building a telescope sensitive enough to detect these signatures from planets orbiting other stars. Roman's coronagraph is a critical step in proving that level of precision is achievable in space. Every measurement Roman's coronagraph makes, every data point on how precisely starlight can be suppressed under real space conditions, feeds directly into the engineering of the future mission. Roman is the proof of concept. What works gets incorporated, what falls short gets redesigned. This is why Roman's coronagraph matters, even if it never images an Earth-like planet directly. The instrument does not need to find life, to change the course of the search for life. It just needs to work. Roman's planetary census adds the second piece to the bridge. If its survey reveals that Earth-like planets in Earth-like orbits are common, that tells the astronomy community the investment in a life-finding telescope is statistically justified. The targets are out there. The the question is worth the cost. Whether Earth-like planets in habitable zone orbits are common or rare across the galaxy is currently unknown. Roman census is the most direct measurement ever designed to resolve this. And that answer matters enormously for what comes next. Nancy Grace Roman built the institutions that made Hubble possible. Hubble built the case for Webb. Roman builds the case for the observatory that may finally answer whether anything in the universe is looking back at us. Each generation of astronomers builds the telescope the next generation needs, and what the next one finds, using the tools Roman proves work in skies Roman has already mapped, may be the most important discovery in human history. The final chapter of Roman's story is not the end of the search. It is the moment the search truly begins. 5 years from now, if Roman launches and operates as designed, humanity will possess knowledge about the universe that no previous generation has ever had. Not beliefs, not theories. Measurements. Precise, statistically powerful, observationally grounded answers to questions that have been open for decades. Here is what we will know. We will know whether dark energy is constant or changing across cosmic time. Not as a hint from a limited dataset, but as a measurement across tens of thousands of supernovae, hundreds of millions of galaxies, and baryon acoustic oscillations spanning nearly the full history of the universe. These are confirmed science goals of the Roman mission, designed into its survey strategy from the beginning. If dark energy is evolving, Roman will find the deviation. If it is constant, Roman will confirm it with enough precision to settle the debate for a generation. We will have a complete statistical picture of planetary demographics across our galaxy, covering orbital distances and planet masses no previous mission has reached. We will know how often planets appear in habitable zone orbits. We will know how common free-floating planets are, and what that tells us about the violence of solar system formation on average across the galaxy. We will have the most detailed map of dark matter ever assembled, tracing its distribution from galaxy cluster scales to the vast cosmic web across billions of years of gravitational evolution. If dark matter behaves differently from what our models predict, that mismatch will show up in Roman's weak lensing data. We will have proven, in space, whether the coronagraph technology needed to eventually photograph Earth-like planets around other stars performs as designed. That proof will determine the path of the search for life for the generation that follows. And here is what no science plan can account for. Based on the history of every large observatory ever operated, Roman will almost certainly find something no one predicted. Something that does not fit the best models in cosmology. Something that points toward physics beyond what we currently understand. What that something will be is, by definition, unknown. But statistically, it would be extraordinary if it did not exist somewhere in 5 years of data covering 1 billion galaxies. That unexpected discovery may not be identified immediately. It may not be flagged until years after the mission ends, when researchers working through the public archive notice a pattern no one caught at first. That is how the deepest discoveries often work. The data exists. The explanation takes time. Nancy Grace Roman spent her career building the instruments and institutions that let future scientists see further than she could. The telescope named for her will do the same. It will hand the next generation a dataset rich enough to work with for decades, a map of the cosmos at a scale never previously attempted, and answers to questions that have been open since the beginning of the space age. The camera that covers more sky than the full moon is almost ready, 1 million miles from Earth, pointed at everything, looking for answers to the oldest questions we know how to ask. The universe has been waiting. Roman is nearly there.